So thank you for coming. This is Modules and Services. My name is Alex Buckley. I work in the Java Platform Group at Oracle with Mark and Alan. This is the fourth of 5 modularity talks at Java 1. The fifth one is, I'm also doing Project Jigsaw under the hood in this room, I believe 4:30 today. So modules and services, this is going to be very interesting because this is an aspect of the module system that we have never talked about in public before. It's been documented in public, there's an implementation, but we've never actually presented on it or explained the backstory of how you can use it. So before I get started, I would like to do a straw poll. If I said metainf/services, who would know what I meant? A few, maybe 15 hands, okay, 16 hands, good. If I said Java util service loader, who would know what that is? Actually, a few more hands. That's interesting. A few more hands who know about the service loader API than the meta services that drives it. Okay. Who has built an application that calls service loader? Okay, probably the same hands as a little bit earlier. Okay, so even in this room, a minority, so that's good. So I often say that modules are quite different than language features like, say, lambda expressions. Lambdas are about the shape of programs in the small, individual for loops turning into method calls with lambda arguments. You can reshape a program to use lambdas really without anyone noticing. Modules are about the shape of programs in the large. We deal with classes and packages and get bigger from there. If you reshape a module, it's quite likely that other people will notice. And although modules are expressed in the Java language, they are in some ways outside the language. They define architecture more than code. I say this because services are the purest form of architectural construct offered by the module system. They're something you have to design for very explicitly. It's possible that in your daily work, you will never come across services. But you're here now. So let's talk about 3 things. What services are, what they can do, and how they work behind the scenes. So, what services are? When we talk about modules, we typically talk about 2 things, module dependencies and package exports. Java Desktop is the JDK module that contains AWT and Swing. As you can see, it expresses a dependency on the Java XML module, so it can access all the public types in the API exported by Java XML. And it exports the Java AWT package so that anyone who requires Java Desktop can access the public types of the Abstract Windowing Toolkit API. So the coupling between Java Desktop and its dependency, Java XML, is very tight. If Java XML isn't found at compile time, then Java Desktop on the slide can't be built. And at runtime, if Java XML isn't found, then no system depending on Java Desktop can start, since Desktop's dependency on XML would be unresolved. There's another kind of coupling between modules that is much looser. It's so useful that we've built it into the module system. It involves one module requesting an implementation of an interface. That's blue. You're going to be seeing a lot of these colors. And other modules providing implementations of the interface. For example, in real life, the Java Desktop module can request an implementation of the print service lookup interface, while some other module outside the JDK, printlib, has some class that implements print service lookup. At runtime, code in the Java Desktop module can call a simple standard API to obtain an instance of print service lookup. The instance is of class fastprint in the printlib module, from the printlib module. But Java Desktop does not require printlib. This means Java Desktop can be resolved by the module system even if printlib is not present. Also, printlib does not export the package that contains this fastprint class. Fastprint, the class, is not an API that other modules should access directly. Other modules should invoke methods of fastprint only through the print service lookup interface. What do the module declarations look like? Very simple. Java Desktop, the requester, uses print service lookup, and printlib provides it with fastprint. Print service lookup is the service type. The service type is usually an interface, but it can be an abstract class or even a concrete class if you really have a need for that. Fastprint is the provider class. The provider class must be a concrete class that implements or extends the service type and declares no args constructor. We say that Java Desktop is the consumer module and printlib is the provider module. Notice in Java Desktop, it's very interesting, you're seeing requires takes a module name, Java XML, exports takes a package name, Java AWT, and uses takes a type name, Java X print service lookup. 3 different properties of a module, 3 different keywords, 3 different kinds of arguments. In printlib, the provide statement takes 2 type names, one for the service type and one for the provider class that's implementing it. This provides clause is the modular equivalent of a file called metainf/services/javax.print service lookup that lists com printlib fastprint. If a jar has a module info.class file, as printlib would, then any files in metainf services are ignored. The module declaration wins. Now, just to clarify, there's no dependency injection going on here. If your module, let's say your Java Desktop, if you say uses S, you use some service type, and you have a field of that service type, then it's not the case that an instance of that type S is magically assigned to the field. You have to ask for an instance of the service type explicitly, as Java Desktop will on the next slide. To obtain an instance of print service lookup, code in the Java Desktop module employs the service loader API introduced in Java SE6. The key method in service loader is load. Load takes a class object representing a service type, print service lookup.class. As long as Java Desktop says that it uses print service lookup, the load method returns a service loader object capable of yielding instances of that service type. Now, there might be more than one provider module for print service lookup, which means more than one provider class. Each instance that service loader yields of the service type is of a different provider class. Helpfully, the service loader object, service loader implements iterable, so you can for each your way through the available instances of these provider classes, looking for one that you like. In this case, Java Desktop hopes to find a print service lookup implementation that offers some kind of specialist print service involving a doc flavor. I don't know what that is, but it's a thing on print services. If service loader yields no instances of print service lookup, or if it did, but none could offer this specialist doc-flavored print service desired by Java Desktop, then Java Desktop decides to return some default print service object. Now, this code would typically live in a static method of the service type, so that print service lookup is its own factory. Before JDK 8, interfaces couldn't have static methods, so most service types were abstract classes. But now that interfaces can have static methods, it's more common for the service type to be an interface and still offer a static factory method such as this. At this point, everyone asks, if service loader finds all provider classes that implement print service lookup and yields an instance of each one. How does Java Desktop specify that fastprint is my favorite implementation of print service lookup? Alternatively, how does the printlib module specify that my class fastprint is the best implementation of print service lookup? Trust me on this. The other question everyone asks is about ordering. How does Java Desktop specify that it prefers the fastprint implementation of print service lookup to this netprint implementation at the bottom, but it's happy to run with netprint if fastprint is not present? Now bear in mind that provider modules usually, like printlib and netprint, usually don't know about each other. So they can't reasonably be involved in selecting or sorting implementations. The consumer module, Java Desktop, is obviously the right place to do it. But discussions around this quickly lead to complicated schemes that encode provider preferences in a module declaration. Now, we're trying to keep the module system simple. So the answer is, you don't specify a global preference for provider classes, at least not in a module declaration. Instead, the basis for choosing one provider class over another is application dependent. It's a choice the consumer module has to make by inspecting the properties of available provider classes. And by properties, I don't mean reflecting over their fields. I mean calling methods of the service type on every instance of a provider class. Recall that Java Desktop calls the getDefaultPrintService method on each instance of print service lookup, and then makes further calls on the result to decide if the instance is acceptable. The consumer module should not be concerned with the identity of the provider classes. They're private details of the provider modules. In fact, we strongly discourage provider modules from exporting the provider classes, because if they're exported, it encourages people to code outside the interface and directly against the provider class, at which point you've lost the benefit of loose coupling. So my advice is to think of the service type as a slightly coarse-grained selector. A service type should offer enough descriptor methods about the quality of implementation for a consumer module to select the best provider class, or an instance of the best provider class. In our example so far, the service type print service lookup is a proxy for the real objects of interest. There may be many instances of print service lookup on a system, each one representing many instances of print service, but able to offer a default print service to consumers. In another scenario, the service type might directly represent an object of interest. In this example, actually, the print service interface offers possibly a rich enough set of descriptor methods about flavors and supported things that it could perhaps in itself be a legitimate service type. How much abstraction you design into your service type depends on the application. The main factor is how heavy the ultimate objects of interest are. For example, if the nature of a print service at the bottom, if the nature of a print service is that instantiating one might be slow, perhaps because a provider class might be expected to scan the network looking for printers. The module was called netprint earlier. Then there's value in print service lookup instances to act as proxies or wrappers that decide whether a print service instance is actually available. But if the nature of a print service is that it's cheap and easy to instantiate, then the value of print service lookup as a service type is diminished. It's very interesting to look at the service types consumed by the Java Desktop module. The service types in blue, yep, that looks pretty good. In blue are proxies or factories or wrappers if you prefer. Print service lookup is among them. The type next to it, stream print service factory, is the same deal. And looking at the top, you would call methods on instances of input method descriptor in order to find the instance that offers the desired input method. And you would call methods on instances of image input stream SPI to choose one that can best convert your data to an image input stream. That will be the ultimate object of interest. The Java doc for the 5 SPI types near the top even says, the intent is that it be relatively inexpensive to load and inspect all available provider classes. These classes may then be used to locate and instantiate more heavyweight classes that will perform actual work, in this case instances of image reader, image writer, image transcoder, image input stream, and image output stream. The service types in brown are not proxies, but rather the classes for the actual objects of interest, while MIDI device provider in blue is just a proxy for obtaining MIDI device objects. MIDI file reader in brown is real business logic. A provider class for MIDI file reader knows how to obtain a MIDI sequence from a file. The bottom line is that the service loader API is agnostic about the granularity of your service type, which has the happy side effect of keeping quality of implementation details and provider preferences out of module declarations. At this point, you're probably wondering, where do the service types actually live? A service type is just an interface in a package in a module. That package will almost always be exported from the module so that other modules can require the module and access the service type. So the service type is very widely exported. It's in foo. Foo is not a consumer module or a provider module. Foo is just the guy exporting the service type for people to consume and provide. Then a consumer module needs to access the service type for its uses clause and for the code that employs service loader to get instances of the service type. A provider module needs to access the service type for its provides clause and for the provider class that implements or extends the service type. In general, there can be many consumer modules and many provider modules for the same service type. A consumer module will say requires and uses, while a provider module will say requires and provides. The arrows look a bit complicated when they're all drawn out, but browsing the source of module declarations makes it pretty clear what the service relationships are. If you skim the JDK module summary, it's very easy to see which modules are consumers with uses and of what, and which modules are providers with provides clauses and of what. That's a major advance over grepping for service loader.load calls and wondering which jars on the class path have files in metainf/services. All that said, it's not mandatory for a service type to be defined in a different module than the consumer modules and the provider modules. In the JDK, it's quite common for a module which defines and exports a service type to also be a consumer module for that service type. For example, java.desktop exports the Java AWT im_spy package so that other modules can implement the SPI types and act as provider modules. And Java Desktop uses Java AWT im_spy input method descriptor to be able to get instances of those types, of those provider classes. Many well-known frameworks in the JDK, such as logging, file system, and datetime, support this kind of customization via provider modules. That is to say, the JDK modules will use their own service type that's then provided by a third party. It's also relatively common in the JDK for a consumer module to also be a provider module. For example, Java Desktop uses print service lookup, and it provides an implementation in the form of sunprint print service lookup provider. This allows the method in Java Desktop that returns print services, the code before, to be assured that it can always return at least an instance of some default provider class. Ultimately, you can see that a single module, such as java.desktop, may contain the service type and the uses clause to facilitate the code employing service loader, and provides clauses to specify one or more provider classes. I mentioned earlier that a consumer module should choose an instance of the service type by calling API methods on it rather than reflecting over the provider class. However, it's sometimes useful to ask service loader for the provider classes themselves, not so much because you want to reflect over their methods, but because you want to defer creating instances of the service type. To support this use case, we've introduced a nested interface in service loader called provider. When you call service loader.load to get a service loader that implements iterable, you can then obtain a stream of provider objects and filter by provider class to your heart's content. Then, as shown near the bottom, it's only when you call get on a provider object that an instance of the service type is created. That's up to you. A quick note, it's not really that quick, but let's say it's a quick note on documenting services. When a uses clause in blue appears in a module declaration, it's actually describing an implementation detail of the module, rather like a requires clause. The module's employment of service loader to find providers of the used service type is not part of the module's API in the way that exported packages are. However, it's quite likely that the module's behavior depends on whether any provider classes are found, and if so, what their characteristics are. It's usually necessary to document the consumer module's expectations, both on provider modules and on higher level modules that require it. So a uses clause isn't quite as private a detail of the module as a requires clause. Similarly, when a provides clause appears in a module declaration, it's for the benefit of service loader, not for anyone requiring the module. Now, there are certainly scenarios where provider modules are not of general interest, such as where the provider classes implement a service type that's not widely accessible. But usually, the author of a provider module will want to document something about their provider class. So, rather than relying on the @impl_note tag introduced for Javadoc in JDK 8, Javadoc in JDK 9 supports two new tags, @uses and @provides, that allow consumer and provider modules to document their service relationship. Where's my pointer gone? So that's part one. Service relationships are first class in the module system. Programming against service types means that provider classes can be encapsulated. And many JDK frameworks build on services and are customized with them. Let's move on. It should be obvious that services let you plug in implementations that weren't known to your program at compile time. For examples that show that, I recommend the Java 9 modularity book available in early access at the O'Reilly bookstore in the exhibition hall. Is Sander here? Sander, he may even, if you go there at 1:30 today, sign it for you. One thing that's not so obvious is that services are actually the key to encoding a number of sophisticated relationships between modules that might otherwise appear to be unsupported by the module system. In particular, I'm going to talk about how optional module dependencies are neatly encoded with services. As an example, consider the Java scripting module in the JDK. It offers an API to evaluate snippets of code. At runtime, there might be many implementations of scripting languages capable of evaluating snippets written in their own language, such as Nashorn, that's Oracle's implementation of JavaScript, or Groovy, or JRuby, etc. How is the Java scripting module meant to depend on them? It seems like we need a way to say requires optional, so that Java scripting reads whichever modules are available. And if none are available, that will be okay, the module system would still start. That seems like it's what we need. The trouble with a requires optional clause, other than the fact that it's an oxymoron, is that it only makes sense when the Java scripting module has already been built. But suppose you're at compile time. What if source code in Java scripting refers to a class in one of these optional modules, either JDK scripting Nashorn or Groovy script engine, and that optional module isn't present at compile time? It's not acceptable for a Java compiler to proceed when it can't find classes referenced in source code. Nor do we want to relax the Java language with some form of loose dynamic typing. Now, you can get a bit further if you never refer in source code directly to classes in optional modules and instead you access them via reflection. But that's a very painful programming style. It was how you had to code on the Java ME platform when different devices implemented different APIs. It doesn't scale. The proper way to program against 0, 1, or many modules is with services. Services introduce a level of indirection by means of the service type. You can mechanically translate an optional module dependency at the top of the slide to a pair of non-optional dependencies on a module which exports a service type. This decouples the number and identity of provider modules from the consumer module, which is what optionality is all about. And if there is one slide in this presentation that I would encourage you to take a picture of, it is this one. Though many people did, but this is what services are all about, to be honest. Consumer module, provider module, service type indirection, everyone is loosely coupled. Well, the consumer module is tightly coupled to the service type module, so is the provider module, but the consumer and provider modules don't know about each other. That's optionality. Since Java scripting is a JDK module, it won't come as a surprise that it's not only the consumer module, but actually also the home for the service type. At the top, the Java scripting module both uses the script engine factory interface, because it's a consumer module, and actually exports its package. And then further down, the Nashorn and Groovy modules, in this example, each provide an implementation of script engine factory. The module system discovers their role as provider modules during service binding, which I will come on to a little later. Now code in Java scripting can employ Service Loader to get instances of script engine factory and call its methods without worrying where the implementations come from. Script engine factory has many descriptor methods that let provider classes describe the quality of implementation of the script engines that they ultimately offer. Which language is being implemented, the version of that language, how long the snippets can be, all that kind of stuff. The Java scripting module explicitly does not say requires JDK scripting Nashorn or requires Groovy script engine. In fact, if you look closely, you'll see that those modules require JavaScripting because that's where the service type lives in this example. But of course, the service type, in theory, could be somewhere else. In effect, the way that you get optional dependencies is by inverting them. So that's a short part 2. Service relationships are the way to encode module dependencies. Services give then not just loose coupling, but better separation of concerns between the consumer module and the provider modules. And services are almost always, I mean, this should really be obvious, services are almost always a better choice than messing with reflection and class forenaming your way around the world and then seeing what the methods are, etc. I mentioned service binding. Let's talk more about it. You might ask, does the module system really need to be involved in the consumption of service types and the discovery of provider classes? Weren't we just okay with service loader on SE6? Well, it's for 2 reasons, and they should be pretty familiar by now. First, services interact with strong encapsulation. Just because a module has a provider class that implements a service type doesn't mean that the provider class is widely accessible. In all the examples we've seen, a provider module did not export the package where the provider class lives. That means there's no access to the provider class from outside the provider module. You can't new it. Even if you have an instance of the service type obtained from service loader and you call getClass on the instance, you still can't manipulate the instance through the provider class. Your code can only access the instance and reflect on it, if it really wants, through the service type. To support this strong encapsulation of provider classes, the service loader mechanism actually has to break strong encapsulation. It needs to instantiate non-exported classes of arbitrary modules with provides clauses. The service loader mechanism is part of the Java base module, so it has superpowers that let it instantiate provider classes even when not exported. Second, the module system is responsible for checking that a module whose code employs service loader has declared its dependency on the service type with uses. This is part of our reliable configuration story. In general, we think it's good practice for a module to declare how it interacts with the outside world. So in particular, we think it's good practice for a module to declare that it's going to use a service type. This explicit dependency on code outside the module, typically the service type will be in a different module, is also needed to let the module system know that it must look for provider classes at startup. And so we come to the heart of how the module system supports services. Suppose your application consists solely of module A, which contains, exports, and uses the service type I. At startup, the module system searches the module path and the Java runtime image, looking for modules which say provides I with something. This matching of uses to provides is called binding. Now, I'm fond of saying that while the watchword in JDK 8 was functional, the watchword in JDK 9 is transitive. You all know that a module relies on everything in the transitive closure of its requires clauses. With binding, the transitivity takes on a whole new character. That's because a module relies on everything in the transitive closure of its uses clauses too. When the module system discovers that B provides the service type used by A, it tries to resolve B. That means, since B requires C, that means locating C. Obviously, B can only work reliably as a provider module, in fact, as a module at all, if C is found. B requires C. And if C is found, its own implementation may use another service type, so then the module system should try to discover D. In effect, A relies on B and C and D, even though A doesn't require any of them. Now you might be wondering, if C is not found, then B would not work reliably. I think we all understand that. So why not just forget about B as a provider module? Just unbind B from A. We could do that, but it's pretty bad that someone has presented B on the module path without all of its dependencies like C. So in the name of reliability, the module system does not ignore B and move on to another provider, if there is one. It stops. That sounds a bit negative, but it makes for very reliable execution after the binding has been completed. Let's see how this works from the beginning. There will be more slides like that with pictures. Assume there is one root module A. The module system creates a module graph by resolving A's requires clauses. Assume that A requires M and that M doesn't require anything except, of course, java.base. Having resolved A and M, the module system proceeds to bind services for them by inspecting their uses clauses. Let's say this results in modules B and N being added to the module graph. B and N each have their own requires clauses, which the module system resolves. Let's assume B requires C, which just requires java.base. And let's assume that N requires O, which just requires java.base. Having resolved B and C and N and O, the module system proceeds to bind services for them by inspecting their uses clauses. This results in modules D and P being added to the module graph. D and P would each have their own requires clauses, but let's assume we're done at this point. The picture would be more complicated if there were multiple provider modules for any of the service types, or if there were more modules pulled in via requires. But in a way, none of this is more complicated than the dynamic linking that the JVM does for classes. It's just that modules make their linking goals explicit with requires, uses, and provides clauses. Let me go back to this picture before we try to resolve B and N. Rather than B requiring C and N requiring O, let's assume that B and N just require java.base. So we're done with the requires. So with no more light blue requires arrows to add, the module system proceeds to bind services for B and N by inspecting their uses clauses. It might be that B and N are not only provider modules for I and J, maybe they don't require anything, but they're also consumer modules. Binding B and N results in E and Q being added to the module graph via service binding. E and Q each have their own requires clauses as well as their own uses clauses. But really, this time, let's assume we're done. What we've seen is that configuring a module graph involves more than just resolution of requires clauses all the way down. In general, every module can have requires clauses, uses clauses, and provides clauses. The basic process is to resolve all the requires clauses of some set of root modules, then bind uses to provides, resulting in more modules, then iterate with the new modules serving as the new set of root modules. Eventually, no more modules will be resolved for requires or bound for uses. For maximum reliability, we want to do all this once at startup. Being able to perform resolution with binding well in advance of execution is what lets us, if we choose, link modules into a Java runtime image and optimize references between bytecodes in different modules. and it means fewer surprises at runtime from missing modules in line with our goal of reliable configuration. So, speaking of linking modules into a runtime image, we found that services need to be handled carefully. Who here has heard of the jlink tool? In other words, who here was in the keynote? Quite a lot of people. Good. In principle, the jlink tool that combines modules into a Java runtime image performs the same resolution and binding steps as the module system at runtime. But experience has shown that people building a Java runtime image usually want the smallest possible number of modules in it. People were very surprised when jlink performed service binding that pulled in apparently irrelevant modules due to service relationships. For example, running jlink for module A could result in module Q being in the Java runtime image. That surprised people. So as a result, jlink actually does not perform service binding by default as a pragmatic matter. If you want a provider module to be included in your Java runtime image, you need to specify it to jlink with a command line flag. This will cause the provider module to be resolved and anything it requires to be pulled in, but then its own users clauses will not be bound to providers, so you might need more command line flags. Again, that sounds a bit negative, but it fights bloat in your Java runtime image, which if you're running jlink, you probably care about a lot. Nearly there. Let's just finish by talking about migration for a moment. Recall that everything on the class path in JDK 9 is treated as being in the unnamed module. Also recall that the unnamed module acts like it requires all named modules in the JDK image and on the module path. That's for compatibility. For services, the good news is that the unnamed module, with a bunch of jars that are found on the class path, is a provider module. During service binding, the module system scans the meta-inf services files of every jar in the class path to see what the unnamed module provides. When a consumer module employs service loader to get instances of a service type, instances of provider classes in jars on the class path will be returned alongside instances of provider classes in modular jars on the module path and modules in the runtime image. The fact that some provider classes come from the class path is completely transparent to the consumer module. You might recall that we believe strongly in reliable configuration and not letting named modules depend on the arbitrary content of the class path. However, in the case of services, we think it's okay to expose provider classes from the class path because the consumer module always has to be prepared for and select from an arbitrary set of provider classes. If the unnamed module is actually a consumer module, that is code on the class path is employing service loader, then again it's transparent where the provider classes come from. They might come from named modules on the module path or in the runtime image, or from jars on the class path. The unnamed module implicitly has an infinite number of users clauses, so it's permitted to get instances of any service type, such as those provided by named modules. Finally, this slide is deliberately messy to make a point that migration is messy. Recall that you can move a traditional jar from the class path, where it would be in red, to the module path in order to make an automatic module like Guava on the slide. From the point of view of services, an automatic module is very much like the unnamed module. First, like the unnamed module, an automatic module reads all other automatic modules, plus the modules in the Java runtime image, plus the unnamed module for compatibility. Those are the light blue arrows. This means an automatic module is likely to read any modules which export service types. That's always the first step. Second, like the unnamed module, an automatic module has an infinite number of uses clauses. Those are the dark blue arrows. This means an automatic module can employ service loader. It can call service loader to get instances of any service type, and the provider classes can come from the class path, the module path, and the Java runtime image. Third, during service binding, the module system scans the metainf services files of traditional jars on the module path to discover what each automatic module provides. Those are the purple arrows. The bottom line is that for services, whatever worked on JDK 8 should just work on JDK 9, no matter how code is arranged into explicit modules, explicit named modules like Java-based and Java SQL, automatic modules like Guava, and the unnamed module. So I talked about service binding, an iterative process that augments the module graph. Service binding is impressively agnostic to explicit, automatic, and unnamed modules. And it's also somewhat orthogonal as an issue to linking together a Java runtime image. So in sum, service relationships are first class in the module system with users and provides. Services give not just loose coupling, but better separation of concerns, stronger typing. And service binding that makes all this work is agnostic to explicit, automatic, and unnamed modules. That's all there is about services. Let me broaden a little bit and talk about JDK 9 in general. The single best thing you can do to prepare for JDK 9, other than attending all these excellent talks, is to fire up JDK 8 and run the JDEPS tool, which analyzes dependencies. It can tell you if your code or code that you rely on will be affected by changes in JDK 9, such as encapsulating sun types in the JDK. Please try the JDK 9 early access binaries on java.net. The module system has been present and active in these binaries since March 2016. Plus, the JDEPS tool included in JDK 9 builds is more accurate than the tool in JDK 8, 2 years later. Everything you ever wanted to know about the module system is discussed in JEP 261. I cannot emphasize enough how much valuable information is in JEP 261. There's also JEP 260, which defines the JDK internal classes that are actually being exposed in 9. JEP 223, which defines the new version strings beginning with 9 dots. And JEP 220, which describes how rt.jar and friends have gone away. Finally, JEP 200 gives an overview of the JDK modules, but if you've already read JEP 261, which of course you will have done, there won't be any surprises. And with that, thank you very much. Questions, which should be asked from the microphone, or we can't hear because all the people are making lots of noise as they leave. Hello.
Hi. So earlier you talked about the situation where there's a partial compliance with the service, right? So A depends, or yeah. So A wants a service is provided by B, but B cannot be fully resolved, right?
This one.
Yeah. So not clear to me what you meant by the module system stops, because there could be another one, E, that provides that service, and it can be resolved.
Yes. So for simplicity, I've only shown here for any users I've only shown pairs. There could be many provides for users. So it might be that in addition to B providing I, some other guy provides I.
Yeah.
And that other guy has all their dependencies resolved and it's all great. But this provider B that happens to have a lot of dependencies such as C, someone forgot to put C on the system.
Right.
So the question is, should we at that point say, okay, well, B's dependencies couldn't be resolved, so let's just forget about B, just forget it,
Right.
unbind it, and just continuing having bound some other module
Right.
to interface I. You saw how iterative this process gets.
Yeah.
If you ever think of, if you dream of unbinding things, you're going to have to unwind a lot of previously bound and perhaps optimized references between. Because ultimately, all this uses and provide stuff is just set up for a bunch of invoke interface and implements clauses. So if the question is, why don't we just unbind B when its dependencies fail, it's in the name of reliability. Who put B? You should never have a module on your module path whose dependencies are not fulfilled. Something has gone wrong. It's stupid. If B is on the module path, but C isn't. So it's not a good thing to say, oh, B's here, but someone forgot to put its dependencies along with it, so we'll just unbind B, perhaps recursively. I mean, it gets pretty complicated.
But that's somewhat contrary to the optionality solution that you...
I wouldn't say it's contrary.
I mean, the idea is that module B maybe optionally depends on something.
Yeah,
Right,
well,
so-
this is the thing. I know what you mean, but if B is on the system without its hard requires, I mean, if B, here's the thing. This is a great story.
Okay,
If B has no further dependency.
If you model it this way, then
Right. If this is the thing, you know, it's requires clauses are very natural things. Everyone can imagine the hard I shouldn't say binding, the hard resolution of classes in one module to classes in another, as long as they're exported. Like my very first slide, it's great, but it's so brittle. It's so brittle, and automatic modules help move towards your requires clauses working, because at least you've got a target. If you're writing a module, you need to require something, and automatic modules give you something. But they're still brittle, and then you bring uses and provides into the picture, and you have to work out what the interaction is. And you can see how complicated it gets. You can imagine I mean, really, module A is relying, in some sense, on module P, a mile away. So simplicity is always the name of the game. But I'm glad you're asking. This is a very philosophical question that I'm really glad you're asking, because this has been in Jigsaw for some years. And these module declarations, I pull all of them out of the JDK module summary. I don't need to make up examples. It's great. You can go to the OpenJDK project page for Jigsaw, click module summary. You'll see the uses and provides clauses. So keeping it all manageable is a pretty big goal.
So, in some sense, what I'm hearing is, in some sense, what I'm hearing is, if we didn't have the legacy issue of, you know, older models of Java, meaning Java 8 and earlier, then in an ideal world that started off with Java 9, we would have probably done away with hard requires and gone only with possibly services.
In Java, in a future version of Java in 50 years' time, you might imagine all dependencies. Okay, you are right, but the Java that we have in this century,
practice, that's never
what,
gonna
what,
happen.
what you're really what you're really saying is that dependency injection should be standard in the Java language. The new keyword is injurious, because it binds you to a class that has to be you now depend on, rather than programming to interfaces. And I think Kai and I and you would all agree on that.
Okay, thanks.
Thank you. Hello, Ian.
So a question about the way around optional requirements and the fact that you instead just say, I require a provider, and then I interrogate.
No, you require the
Or,
service
sorry,
type.
require sort of a service factory, and then I interrogate it to say, hey, are you the one I'm looking for? Are there concerns about security that come about from that, where I would like to depend on the Nashorn scripting engine, but I don't want to say that I require it directly. So but then I'm going to look and say, are you the Nashorn scripting engine? Someone else can come along and provide the script engine factory and claim to be that. And is there any way to defend against that?
No. It's all, you know, what's the statement? It has never been, what is it? It has never been difficult in any it has never been the least bit difficult in any programming language to write bad programs. So the service loader API, there's no signing going on here. There's no strong identity of a provider module that gets exposed through service loader.
Okay.
Service loader.load is, how would you describe it, Mark? Pleasingly straightforward.
Thank you.
Another aspect of this, though, is that there's been this assumption for many, many years that if you have access to the class path or the module path when an application starts, then, well, you better be trusted because you can put anything on it. So defending against a situation in which a module path has some, fake adversarial, thing that's pretending to be Nashorn but is actually evil, that's not an attack scenario we're worried about. We have to trust whoever's putting the module path together to only put modules on there that they trust. The real security concerns come in when you're loading untrusted code off the internet from an applet or whatever, or you're loading application WAR files in that you might not necessarily trust completely. Then the security manager comes to play and all this other mechanism. But this is pretty much orthogonal to that.
Okay. Good. Thank you.